In this video, we're going to talk about ionic versus covalent bonds and compounds. So, what are ionic compounds? Let's go over one example. Let's say we have sodium that's going to react with chlorine. Now, sodium has 1 valence electron, and chlorine in its neutral state is going to have 7. What happens in this situation is that sodium is going to donate an electron to chlorine. And as a result of losing an electron, sodium is going to become a positively charged cation. Any charged particle is going to be called an ion, and a positively charged particle is going to be called a cation. Chlorine, as a result of gaining 1 extra electron, is going to be a negatively charged anion. So negative ions are going to be called anions. Now, if we have 2 of the same charges next to one another, they're going to feel a force, an electrostatic force, that is going to repel them. But if you have 2 charges that are the opposites, they're going to feel force that is going to attract them. So in this case, we have opposite charges, so they are actually going to attract one another, and that's going to be the bond that is going to be formed. Now, generally speaking, in ionic bonds, you're going to have a metal and a nonmetal. Now, how do you know what a metal is and a nonmetal is? Look at the top right of your periodic table and take a look at the elements that I've drawn here. So, for example, boron, aluminum, silicon, germanium, arsenic. This line that you see drawn right here, everything to the left of this line is going to be a metal, and everything to the right of this line is going to be a nonmetal. Now, the only exception to this is hydrogen, which is always going to be a nonmetal. Hydrogen is the top left of your periodic table, so it's pretty easy to remember that. Usually, in most cases, in ionic compounds, the metal is going to give 1 or more electrons to the nonmetal, and then the metal will become positively charged, and the nonmetal will become negatively charged. And then, as a result of those charges, they're going to attract and form what is called an ionic bond. In the situations we've looked at so far in ionic bonds, they've usually had 1 metal element bonded to 1 nonmetal element, which means that the metal would be made of, for example, 1 type of metal. In other words, let's just say potassium, and then the nonmetal would be something like bromine, where it's 1 type of element. However, what if one of these metals or nonmetals were made of more than 1 element? What would happen then? So that's where we get into polyatomic ions. So there are situations where you can have a metal that is bonded to a polyatomic negatively charged polyatomic ion, which is going to replace the negative nonmetal. Now, just to be clear, polyatomic ions are all made out of, for the most part, all made out of nonmetals, but they are negatively charged. There are also situations where the metal is replaced by a polyatomic ion, and the polyatomic ion may be, polyatomic ion is usually going to be made of completely nonmetals. The last type of situation that we would have is if you have a positively charged polyatomic ion that is going to bond to a negatively charged polyatomic anion. So, polyatomic ions, there are lists of them online, but I'm going to put a list here of some of the more important ones that you're probably going to want to memorize for your chemistry class. So C2H3O2, that one is called acetate. And when I put a negative, that means it's -1. It has a charge of -1. There's only one that's positive, as you can see. It's a +1 charge called ammonium. And these are all the ones that you should memorize. There may be a few more for your chemistry class, but these are going to be the ones that are likely going to be included. So an example could be calcium carbonate. Calcium is a metal with a +2 charge, and carbonate is a polyatomic ion with a -2 charge. This means that calcium has donated 2 of its electrons to carbonate, and as a result, calcium has gained a +2 charge and carbonate has gained a -2 charge. And so because one has a positive charge and the other one has a negative charge, the electrostatic force of attraction will attract these two toward one another. You can also write it out as CaCO3, and your professor or teacher might want you to put the little charges on it. There are actually charts on the internet. I'll leave a link to one in the first link in the description, where it will show you what the charges for most of the metals are, so that you know, for example, that lithium, sodium, potassium, rubidium, and the rest of the elements in group 1 of the periodic table have a +1 charge when they are in ionic compounds, and that the row 2, they usually have +2 charges. Now, when you move to the right of these metals, you're going to get to what's called transition metals. Transition metals, some of them can actually have multiple charges. So for example, one iron can have a +2 charge and another iron might have a +4 charge. There are also charts for those, and I'll leave a second link in the description for that. Now when it comes to nonmetals, they too like to have set charges, and so we're going to go over those right now. When you look at the right of your periodic table and you look at where boron is sometimes considered to be a metal. It's not really a metal. It's sometimes considered to be a non-metal, sometimes considered to be a metalloid. It's sort of in between. And so if you look at this row right here, row 3A, if these are going to be non-metals, they're going to, well, they actually usually act as metals. These would have a +3 charge. And then when you get to row 4, these can either have a +4 charge or a -4 charge. So it'd be carbon, silicon, germanium, lead. That's really the dividing line between metals and nonmetals. The next row is going to be that of nitrogen, phosphor, arsenic, and bismuth, and these are going to have -3 charges. Oxygen, sulfur, selenium, and polonium, and I think that's tellurium, they have -2 charges when they are in ions. And then hydrogen, it's not really part of this group, but if it is going to be negative, along with all the halogens like fluorine, chlorine, bromine, iodine. I drew the eye pretty bad. These are going to have -1 charges. And then the ones that are on the right side, these are called the noble gases. These are usually going to be neutral. They're not going to really form ionic bonds. And at least not that they're common enough to the point where you will talk about them a lot in chemistry class. So now let's, for a last example, let's go through an ionic compound that has all polyatomics. So let's say we have ammonium, which has a positive 1 charge, and let's say we have hydroxide, which has a negative 1 charge. In this example, all of the elements within this ionic compound are technically nonmetals. Nitrogen is a nonmetal, so is hydrogen and oxygen. However, it's an ionic compound because it contains polyatomic ions. This is why it's important for you to memorize that list. And there are actually some covalent bonds within this compound. However, it's ionic because it contains, there's an ionic element to it because it's made up of ions. So this is ammonium, which is this right here. And all of the bonds within this ammonium are covalent bonds. This is covalent, all the 4 are covalent. However, this molecule has an overall positive 1 charge, so that makes it an ion. The hydroxide, the same story is true. All of the bonds within this molecule, there's only one. It's covalent. However, because there are more electrons than protons, it has a negative 1 charge. And since this is a positive charge, this has a negative charge, they're going to attract and they're going to form an ionic bond, and that's why it's called an ionic compound. So that's it for this video. I hope it was helpful and that you learned something. Thank you for watching. Now, what about covalent bonds? Let's take an example of a covalent bond. So let's say we have a hydrogen atom with 1 valence electron, and let's take another hydrogen atom with 1 valence electron. Each of those hydrogen atoms are going to donate 1 electron to the middle, and then a bond is going to form between the 2 hydrogens. And the bond is going to be 2 electrons. Now, in this case, since the atoms that make up the covalent bond are the same atom, they are both hydrogens, this is classified as a nonpolar covalent bond. The reason is that the electronegativity value of hydrogen is 2.1. And so the electronegativity of the other hydrogen is also 2.1. So the electronegativity difference is going to be 0 when you have a covalent bond between 2 atoms of the same elements. I'm going to explain what electronegativity means in a minute and how a covalent bond can be polar. But first, keep something in mind. Covalent bonds usually happen, almost always happen, between a nonmetal and another nonmetal. A nonmetal will donate 1 electron, and the other nonmetal will donate another electron, and there will be a bond made up of 2 electrons that's represented as a line. Now, there can be situations in which one nonmetal donates both electrons, and the bond created between them, it comes from 2 electrons that come from one nonmetal. So now let's say we have a bond between a hydrogen atom and a fluorine atom. What's going to happen is that each of these are going to donate one electron, and then they're going to form a bond made up of those two electrons. They're basically sharing those two electrons. Now, last time in our covalent bond, we had the same elements on each side of the bond, hydrogen. But in this case, we have different elements. And so we can't say for sure that this is a nonpolar covalent bond. What we need to do is look at our electronegativity values. The electronegativity of hydrogen is 2.1, and the electronegativity of fluorine is 4.0. This number right here, electronegativity, represents the strength by which the atom is going to pull the electrons in this bond toward itself. So if we have two hydrogen atoms that are bonded, they are sharing these electrons equally because they're both pulling at the electrons with a strength of 2.1. However, in the example on the top, where you have a hydrogen on one side pulling the electrons toward itself with a strength of 2.1, and the fluorine pulling the electrons toward itself with a strength of 4.0, the electrons are going to be unequally shared. They're going to be a little bit closer to the fluorine and a little farther away from the hydrogen. So, when the electronegativity difference is higher than 0.5 or equal to 0.5, the bond is going to be a polar covalent bond. And when the electronegativity difference is smaller than 0.5, it is going to be a nonpolar covalent. The way we can denote this, one way is to say that hydrogen has a partial positive charge because the electrons are a little further away from it, and fluorine has a partial negative charge. We can also draw the dipole moment where the arrow points toward the direction in which the electrons are pulled a little bit toward. Whenever you have one side of a molecule, let's say this is a molecule, whenever you have one side that is negatively charged and you have another side which is positively charged, this is going to mean that the molecule is polar. The overall charge may still be net zero, but there is a positive charge at one end and a negative charge at another end. Just like we have here, this is technically a neutral molecule overall. However, one end has a negative charge, the other end has a positive charge, and therefore it is considered to be a polar molecule. Now let's say we have a bond between a carbon and a hydrogen. Is this bond nonpolar covalent or is it polar covalent? The electronegativity value of carbon is 2.5, and the electronegativity value of hydrogen is 2.1. So the electronegativity difference between these two is going to be 2.5 minus 2.1, which is 0.4. And 0.4 is smaller than 0.5. So therefore, this bond is going to be a nonpolar covalent bond. So this tells you that every time you see carbon and hydrogen bonded to one another, it is going to be a nonpolar covalent bond. And if you have a molecule which only has carbon and hydrogen, it is also not only going to have nonpolar covalent bonds, it's also going to be a nonpolar molecule. Now, just because there are polar bonds, that doesn't mean the molecule is going to be polar. And we will go through an example where that's the case. However, if you have a molecule where all the bonds are nonpolar, then the molecule itself is always going to be nonpolar. So let's look at an example where carbon is covalently bonded to 4 chlorine atoms. If we look at one of those bonds, fluorine has an electronegativity value of 4.0 and carbon has an electronegativity value of 2.5. Therefore, the electronegativity difference is actually going to be 1.5, which is higher than 0.5. So therefore, this is a polar covalent bond. And since all the bonds in this molecule are between carbon and fluorine, they are all going to be made of polar bonds. So these fluorines are going to have a partial negative charge, and this carbon is going to have a partial positive charge. And the dipole moment is always going to point toward the fluorines. You don't have to denote these in every Lewis structure, but I'm doing it here just to teach something about this. So all of the bonds in this molecule are polar. However, does that mean that the molecule itself is polar? It doesn't mean that. So remember, in order for a molecule to be polar, it has to have a positive end and a negative end. In this molecule, that isn't really the case. There's no one end of the molecule that is positive, and there's no one end that is negative. Instead, the surroundings of the molecule are all negative, and in the middle is positive. That would be a situation that looks more like it would look more like this and not this. This would be a polar molecule, and this would be still a nonpolar molecule even though you have polar bonds. So now let's go through an example where there are nonpolar bonds and the molecule itself, actually no, where there are polar bonds and the molecule itself is also polar. So in water, the oxygen has an electronegativity value of 3.5, and the hydrogen are going to have an electronegativity value of 2.1 as always. So the electronegativity difference is going to be 1.4, meaning that this is a polar covalent bond, the bond between hydrogen and oxygen. Actually, I drew it wrong. It should be toward the negative end of the bond. But now the question is this: is this a polar molecule or not? When you look at the shape of water, this bottom end is positive and the top end is negative. So if I draw it again kind of like a battery, it would look like this, and that is polar. But if I take another example where we have boron and then we have fluorines. Now, boron has an electronegativity value of 2.0 and fluorine has 4.0. So all of these bonds are going to be polar. However, does that mean this molecule is polar? Not exactly, because these 3 bonds are surrounding the boron. Actually, that was wrong, sorry. the negative ends are surrounding the positive end. So it would more look like, sort of be like this and not like that. So it would be a nonpolar molecule even though it has polar bonds. If we look at one more example, let's take ammonia. So ammonia has a nitrogen in the middle, and it has 3 hydrogens, and it also has a lone pair. Now the question is this: is this a polar molecule or is it not? Nitrogen's electronegativity, based on most textbooks, is 3.0. So if that of hydrogen is going to be 2.1, then 3.0 is going to make a difference of higher than 0.5. So these bonds are indeed polar. The other direction, sorry. They're always going to point toward the more electronegative atom. And nitrogen is going to have a partial negative charge. It really is more supposed to look like that. Not really supposed to look like an 8. But that doesn't matter too much. In this case, is the molecule a polar or not? In this case, it actually is a polar molecule, because it looks more like this. Since it has a lone pair, all of these hydrogens are going to get pushed sort of to one side. So it's going to look something, in terms of its charges, going to look like this. However, in the last example, the boron and the fluorines, it looked more like this, where it was surrounded by the negative charges. However, in here, one end is clearly positive and the other end is clearly negative, when such thing is not happening with ammonia. So I know that this can be a little bit confusing, but I hope this clears up some of the confusion and makes this a little bit easier on you when you are in our classes. So now let's go a few more practice problems to understand this concept. Let's say we have carbon, and then we have a chlorine. Now, to be clear, chlorine has an electronegativity value of, I believe, 3.0. Chlorine has an electronegativity of 3.0. Carbon is 2.5, and then hydrogen is 2.1. Now, as we talked about, the bonds between hydrogen and carbon are always going to be nonpolar. However, this chlorine right here, the electronegativity difference between it and the carbon is going to be 0.5, because 3 minus 2.5 is 0.5. So it is going to reach that threshold of 5 and technically be counted as a polar bond. And so what is going to happen is that one end of the molecule is slightly positive and the other end is slightly negative. So in this case, you do have a polar molecule.